In this video, we're going to talk about the two common forms of the equilibrium constant, Kc and Kp. And when we write the C, we're going to involve concentrations, and when we write the P, we're going to involve partial pressures. So let's take an example of an equilibrium of SO3 in equilibrium with SO2 and oxygen. So all of these are gases. We can actually write two different equilibrium constants. We can write Kc, which would be the molar concentration of SO2 squared, because it's got a coefficient of 2 in the chemical equation, the molar concentration of oxygen to the 1, because it's got a coefficient of 1, and divided by the concentration of SO3, and because there's two of them, we can square it. And in Kp, we would do exactly the same thing, but we would use the partial pressures instead of the molar concentration. So a partial pressure, we just write P, and then the thing down below we are referring to. So remember, the partial pressure is the pressure the gas would exert if no other gases were present. So although you got SO3, SO2, and O2, the pressure that SO2 would exert all by itself would be its partial pressure. And again, we are going to square it, so we write the two up there, and we multiply by the partial pressure of oxygen to the 1, and divide it by the partial pressure of SO3 to the 2, because there's two of them. So it's exactly the same equilibrium constant expression, although we just switch concentrations when we use Kc for partial pressures when we write Kp. Now, one last thing to mention here, and we always measure the partial pressures in terms of atmospheres. So we always use atmospheres here. And for the concentrations here, we're always using moles per liter here. And in fact, in these equilibrium constants, we just use the numbers themselves typically. So more on this later, but remember, the partial pressures we're always going to use in atmospheres. Now, in general, they're not equal to each other. So in general, Kc is not the same as Kp. It turns out it can occasionally, but it often is not. Now it turns out we can form a relationship between them, and it's actually kind of a little nice bit of math here. And here goes. The concentration of A, so the molar concentration is the number of moles of A divided by the number of liters. So if we let N be the number of moles and V be the number of liters, right, then we can go ahead and write it like so. Now, for an ideal gas, remember, for an ideal gas, PV equals nRT. And if we're dealing with partial pressures, we can just substitute the pressure for the partial pressure and the number of moles for the number of moles of that component. So PV equals nRT, or PAV equals nART. Now we want to form a relationship here. So we can go ahead and we can solve for NA over V. So NA over V is equal to, let me see, PA divided by RT. So I am just dividing both sides by RT. That clears that side and brings it down there, and I'm dividing both sides by V, and that gives me N over V. So I can look in my expression up here, and I can say the concentration of A is equal to the partial pressure of A divided by RT. So I can see there's a very nice relationship here. Or if you prefer, you can say the partial pressure of A is just equal to the concentration of A times by RT. That's another very easy form to remember. So now we're ready to go ahead and see what the relationship is between the two equilibrium constants. So let's go to a new slide and take a look-see. So let's assume we've got an equilibrium. Let's just make things easy here. We got AA, that's a gas, go into form BB, that's also a gas. And we know that Kp is equal to the partial pressure of the right-hand side, so B raised to the stoichiometric power B, divided by the partial pressure of A raised to the stoichiometric power A. And we saw in the last video that the partial pressure of something is equal to the concentration of something times by RT. So the partial pressure of B would be the concentration of B times by RT, and the concentration of A, the partial pressure of A would be equal to the concentration of A times by RT. Now, if the coefficients were 1, we'd be said and done, but because the coefficients are not 1, then we've got to raise the top to the B and the bottom to the A. In fact, we can go ahead and we can just kind of rewrite that. That's equal to the concentration of B to the B over the concentration of A to the A times by RT to the B over RT to the A. In fact, this first term here we can recognize is equal to just Kc. And the last time term, that is RT to the B over RT to the A. So that is RT to the B minus A. And in fact, if we just go ahead and define here the change in number of molecules of gas in our equation to be just the number of molecules of gas on the right-hand side minus the left-hand side, that allows us to write this expression even more succinctly. So Kp is equal to Kc times by RT to the change in number of molecules of gas. We can see if the change in number of molecules of gas is 0, then a 0 here, anything raised to the 0 is just 1, so Kp and Kc would be exactly the same. But as soon as there's a different number of molecules of gas on one side than the other, they are not equivalent to each other.